Section 3 of Histology of the Blood. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Reading by BellonaTimes. Histology of the Blood by Paul Ehrlich and Adolf Lazarus. Translated by M. Myers. Section 3. B. Normal and pathological histology of the blood. In satisfactorily prepared dry specimens, the red blood corpuscles keep their natural size and shape, and their biconcavity is plainly seen. They present a distinct round homogeneous form of about 7.5 microns in diameter. They are most intensely colored in a broad peripheral layer, and most faintly in the center, corresponding to their depression. With all stains mentioned above, the stroma is quite uncolored, and the hemoglobin exclusively attracts the stain, so that for a practiced observer the depth of stain gives a certain indication of the hemoglobin equivalent of each cell, and a better one than the natural color of the hemoglobin in the fresh specimen. Corpuscles poor in hemoglobin are easily recognized by their fainter staining, especially by the still greater brightness of the central zone. When somewhat more marked, they present appearances which from the isolated staining of the periphery, Litton has happily named pessary forms. The faint staining of a red corpuscle cannot be explained, as E. Grawitz assumes, by a diminished affinity of the hemoglobin for the dye. Qualitative changes of this kind of the hemoglobin expressing themselves in an altered relationship towards dyes do not occur, even in anemic blood. If in the latter the blood discs stain less intensely, this is due exclusively to the smaller amount of hemoglobin. A diminution in the hemoglobin content can in this way be shewn in all anemic conditions, especially in post-hemorrhagic, secondary, and chlorotic cases. On the contrary, as Lach first observed, in the pernicious anemias, the hemoglobin equivalent of the individual discs is raised. To appreciate correctly pathological conditions, it must always be borne in mind that in normal blood the individual red blood corpuscles are by no means of the same value. Step by step some of the cells are used up and replaced by new. Every drop of blood contains side by side the most various stages of life of fully formed erythrocytes. For this reason, influences which affect the blood, provided their intensity does not exceed a certain degree, cannot equally influence all red corpuscles. The least resistant elements, that is, the oldest, will succumb to the effect of influences, to which other and more vigorous cells adapt themselves. To influences of this moderate degree belongs without doubt the anemic constitution of the blood as such, the effect of which is in this direction one can best investigate in cases of post-hemorrhagic anemia. In all anemic conditions we observe characteristic changes in the blood discs. A. Anemic or polychromatophil degeneration. This change in the red blood corpuscles, first described by Ehrlich, to which the second name was given later by Gabritschewski, is only recognizable in stained preparations. The red blood discs, which under normal circumstances stain in pure hemoglobin color, now take on a mixed color. For instance, the red corpuscles are pure red in preparations of normal blood, stained with hematoxylin eosin mixture, but in preparations of blood of achromic anemia, stained with the same solution, in which possibly all stages of the degeneration in question are present, one sees red discs with a faint inclination to violet, others which are bluish red, and at the end of the series forms stained a fairly intense blue, in which scarcely a trace of red can be seen, and which by their peculiar notched periphery are evidently to be regarded as dying elements. Ehrlich put forward the theory that this remarkable behavior towards dyes indicates a gradual death of the red blood corpuscles, that is of the old forms, leading to a coagulation necrosis of the discoplasm. The latter takes up, as is the case in coagulation necrosis, the proteids of the blood, and acquires thereby the power of combining with nuclear stains. At the same time the discoplasm loses its power of retaining the hemoglobin, and gives it up to the blood plasma in ever increasing quantity as the change proceeds. Hence the disc continues to lose the capacity for the specific hemoglobin stain. Objection has been raised to these views from many quarters, especially from Gabritschewski, and afterwards from Askanazy, Dunan, and others. The polychromatophil discs are not, they say, dying forms, but on the contrary represent young individuals. The circumstance that in certain anæmias the early stages of the nucleated red corpuscles are variously polychromatic was evidence for this opinion. In view of the great theoretical importance which attaches to this subject, the grounds for regarding this change as degenerative may be here shortly brought forward. 1. The appearance of the erythrocytes which shew polychromatophilia in the highest degree. By the notching of their margins they appear to eyes practised in the judgment of morphological conditions in a stage almost of dissolution, and as well pronounced degeneration forms. 2. The fact that by animal experiment, for instance, in inanition, their appearance in large numbers in the blood can be produced. That is, precisely in conditions where there can be least question of a fresh production of red blood corpuscles. 3. The clinical experience that in acute losses of blood in man these staining anomalies can be observed in numerous cells within so short a time as the first 24 hours. Whilst in our observations, which are very numerous upon this point, embracing several hundred cases, and carried out with particular care, no nucleated red blood corpuscles in this space of time can be found in man. 4. The polychromatophil degeneration can frequently be observed in nucleated red blood corpuscles, particularly in the megaloblasts. This fact can be so easily established that it can hardly escape even an unpractised observer, and it was sufficiently familiar to Ehrlich, who first directed attention to these conditions. The fact that the normoblasts, which are typical of normal regeneration, are, as a rule, free from polychromatophil degeneration, gave the key for the interpretation of this appearance. And similarly for the nucleated red blood corpuscles of lower animals. Askanazy asserts that the nucleated red blood corpuscles of the bone marrow, which he was able to investigate in a case of empyema, shew, immediately after the resection of the ribs, complete polychromatophilia. This perhaps depends on the peculiarities of the case, or on the uncertainty of the staining method. Eosin methylene blue stain, which is for this purpose very unreliable, since slight overstaining towards blue readily occurs. We expressly advise the use of the triacid solution or of the hematoxylin eosin mixture for the study of the anemic degenerations. After what has been adduced, we hold in agreement with the recent work of Pappenheim and Maragliano that the appearance of polychromatophilia is a sign of degeneration. To explain the presence of erythroblasts which have undergone these changes, we must suppose that in severe injuries to the life of the blood these elements are not produced in the usual fashion, but from the very beginning are morbidly altered. Analogies from general pathology suggest themselves in sufficient number. B. A second change that we find in the red blood corpuscles of the anemias is poikilocytosis. By this name a change of the blood is denoted where, along with normal red blood corpuscles, larger, smaller, and minute red elements are found in greater or less number. The excessively large cells are found in pernicious anemia, as Lach first observed, and as has since been generally confirmed. On the contrary, in all other severe or moderate anemic conditions, the red corpuscles shew a diminution in volume and in their amount of hemoglobin. This contradiction, which Lach first mentioned but was unable to explain, has found a satisfactory solution in Ehrlich's researches on the nucleated precursors of the myelocytes and normocytes. See below. The blood picture of the anemias is made still more complicated in that the diminutive cells do not preserve their normal shape, but assume the well-known irregular forms: pear, balloon, saucer, canoe shapes. Nevertheless, in good dry preparations the smallest forms usually still shew the central depression. The so-called microcytes constitute an exception to this statement. These are small round forms to which was allotted in the early days of the microscopic investigation of the blood a special significance for the severe anemias. They are, however, nothing but contraction forms of the poikilocytes, as the crenated are of the normal corpuscles. Consequently, microcytes are but seldom found in dried specimens, whilst in wet preparations they are easily seen after some time. It is further of importance to know that in fresh blood the poikilocytes exhibit certain movements, which have already given rise to mistakes in many ways. Thus, at one time the poikilocytes were considered to be the cause of malaria. More recently the somewhat larger sizes were regarded by Klebs (Pearls) as amoebas and similar organisms. In agreement with Hayem, who from the very first described these forms as pseudo-parasites, a warning must be given against attributing a parasitic character to them. The origin of poikilocytosis, previously the subject of much discussion, is now generally explained in Ehrlich's way. For the mere fact that by careful heating poikilocytosis can be experimentally produced in any blood forces one to the assumption that the poikilocytes are products of a fragmentation of the red blood corpuscles (schistocytes, Ehrlich), and correspondingly the smallest fragments shew the biconcave form in the dry specimen, for they too contain the specific protoplasm of the disc, "which possesses the inherent tendency to assume the typical biconcave form in a state of equilibrium." Qualitative changes in the protoplasm of the poikilocytes are not to be observed even by staining, and one may therefore ascribe to them complete functional power, and regard their production as a purposeful reaction to the diminished number of corpuscles. For by the division of a larger blood corpuscle into a series of homologous smaller ones the respiratory surface is considerably increased. C. A third morphological variation which anemic blood may shew in the more severe degrees of the disease is the appearance of nucleated red blood corpuscles. Though we do not wish to enter here upon the latest questions concerning the origin of the blood elements, we must shortly indicate the present state of our knowledge of the nucleated red corpuscles. Since the fundamental work of Neumann and Bizzozero, the nucleated forms have been generally recognized as the young stages of the normal red blood corpuscles. Hayem's theory on the contrary, obstinately asserts the origin of the erythrocytes from blood platelets, and has, excepting by the originator and his pupils, been generally allowed to drop. Ehrlich had in the year 1880 pointed out the clinical importance of the nucleated red blood corpuscles, inasmuch as he demonstrated that in the so-called secondary anemias and in leukemia, nucleated corpuscles of the normal size, normoblasts, in pernicious anemia, excessively large elements, megaloblasts, gigantoblasts, are present. At the same time, Ehrlich mentioned that the megaloblasts also play a prominent part in embryonic blood formation. In 1883, Hayem likewise proposed a similar division of the nucleated red blood corpuscles into two. 1. The globules nucleus gigantes, which he found exclusively in the embryonic state. 2. The globules nucleus de taille moyenne, which he found invariably present in the later stages of embryonic life and in adults. Further, W. H. Howell, 1890, found in cats' embryos two kinds of erythrocytes: 1. Very large, equivalent to the blood cells of reptiles and amphibia, ancestor corpuscles, and 2. Of the usual size of the blood corpuscles of mammalia; and similar more recent authors, H. F. Müller, C. S. Engel, Pappenheim, and others, have adhered to the division of hematoblasts into normo and megaloblasts, and it is on the whole recognized that, physiologically, normoblasts are always present in the bone marrow of adults as the precursors of the non-nucleated erythrocytes; that the megaloblasts, however, are never found there under normal circumstances, but only in embryonic stages and in the first years of extrauterine life. S. Eskenazi, on the contrary, has expressed the view that the normoblasts may arise from the megaloblasts, and thereby denies the principal distinction between them. Schaumann also holds that the separation of the two kinds rests on doubtful foundation, since occasionally it is questionable whether particular cells are the normoblasts or the megaloblasts. We distinguish three kinds of nucleated red blood corpuscles on the grounds of the following characters. 1. The normoblasts. These are red corpuscles of the size of the usual non-nucleated disc, whose protoplasm as a rule shews a pure hemoglobin color, and which possess a nucleus. Occasionally there may be 2 to 4 nuclei. The sharply defined nucleus lies generally in the center, comprises the greater part of the cell, and is above all distinguished by its intense color with nuclear stains, which exceeds that of the nuclei of the leucocytes, and indeed of all known nuclei. This property is so characteristic that the free nuclei, which occur occasionally in anemias, and particularly often in leukemia, may be recognized as nuclei of normoblasts, although surrounded by traces only of hemoglobin, or by none at all. 2. The megaloblasts. These are 2 to 4 times as large as normal red blood corpuscles. Their protoplasm, which constitutes by far the chief portion of the body of the cell, very often shews anemic degeneration to a greater or less degree. The nucleus is larger than that of the normoblasts, but does not form so considerable a fraction of the cell as in the latter. It is often not sharply defined, and is of a rounded shape. It is distinguished from the nucleus of the normoblast by its much weaker affinity for nuclear stains, which may often be so small that little practised observers perceive no nucleus. Occasionally very large cells are present, of the kind just described, which are therefore called gigantoblasts, but which are not distinguishable in other respects from the megaloblasts. It cannot be denied that it is often difficult to decide whether a particular cell is to be regarded as a specially small megaloblast or a large normoblast. In such cases one would naturally search the preparation for perfect forms of hematoblasts and for the presence of free nuclei or of megalocytes, in order to obtain an indirect conclusion concerning the cells in question. 3. The microblasts. These are occasionally present, e.g. in traumatic anemias, but they are very seldom found, and have not so far attracted particular attention. The question of the meaning of the normoblasts and megaloblasts has led to lively and significant discussions, partly in favor of, partly against the distinction between these two cell forms. After surveying the literature, we are forced to separate the megaloblasts from the normoblasts, in the first place because of their subsequent histories and the peculiarities of their nuclei, and secondly because of clinical observation. The fate of the nuclei. For some time past, two views, almost diametrically opposed, have been in existence with regard to the nature of the change of the nucleated to the non-nucleated erythrocytes. The chief exponent of the one, Rindfleisch, told that the nucleus of the erythroblasts leaves the cell, which thereby becomes a complete erythrocyte, whilst the nucleus itself, by the aid of the small remnant of protoplasm which surrounds it, takes up new material from the surrounding plasma, manufactures hemoglobin, and so becomes a fresh erythroblast. According to the second theory, the erythroblasts change to non-nucleated discs by the destruction and solution of the nucleus within the cell body. Karyoarrhexis, karyolysis. The authors who support this view, and also describe it as the only kind of erythrocyte formation, are chiefly Kolliker and E. Neumann. Rindfleisch arrived at his theory by direct observation of the process described, as it occurred in physiological saline solution with the blood of fetal guinea pigs and teased preparations of bone marrow. E. Neumann regards Rindfleisch's doctrine as untenable, since the process which he observed is chiefly the result of a severe injury of the blood from the sodium chloride solution and the teasing. If a method of preparation be chosen which protects the blood as far as possible, and avoids every chemical and physical alteration, the exit of the nucleus, as described by Rindfleisch, does not occur. The view of Kolliker and Neumann that the nuclei gradually decay in the interior of the cell is not supported by the observation of a process, but by the fact that in suitable material, for instance fetal bone marrow, liver blood, and leukemic blood, the transition from erythroblast to erythrocyte is shown by all phases of nuclear metamorphosis, versus Recklinghausen professes to have directly observed the dissolution of the nucleus within the cell in rabbit's blood, kept living in a moist chamber. Pappenheim's opinion, however, that in this case processes are concerned such as Maragliano and Castellino have described as artificial necrobiosis, seems in this connection worthy of consideration. Just as with regard to the formation of the erythrocytes, the views differ one from another, so also with regard to the free nuclei which come under observation in numerous preparations. Kolliker has taught that these nuclei are not quite free, but are always surrounded by a minute border of protoplasm. On the other hand, Rindfleisch regards these nuclei as having migrated from or having been cast off by the erythroblasts, and Neumann explains them as early forms of erythroblasts. Ehrlich was the first to endeavor to effect a compromise between the directly opposed views of Rindfleisch and Neumann. He taught that both kinds take part in the production of the red discs. From blood preparations which contain numerous normoblasts, for instance in blood crises, see page 62, an unbroken series of pictures can easily be put together showing how the nucleus of the erythroblasts leaves the cell, and at last produces the appearance of the so-called free nucleus. It must be expressly mentioned that these pictures are only to be found in specimens in whose preparation pressure of any kind upon the blood has been avoided. Further, however rich a blood may be in normoblasts, the metamorphosis of the nucleus as described by Neumann is practically never to be observed. It is quite otherwise with the megaloblasts. Amongst them, few examples are to be found in which traces at least of the destruction and solution of the nucleus are not shewn, and in a blood preparation of pernicious anemia, which is not too poor in megaloblasts, one can construct step by step the unbroken series from megaloblasts with a complete nucleus through all stages of karyorrhexis and karyolysis to the megalocytes, as the process is described by Neumann. From Ehrlich's observations it follows that the normoblasts become normocytes by extrusion or emigration of the nucleus. The megaloblasts become megalocytes by degeneration of the nucleus within the cell. M.B. Schmidt, without making use of the principal distinction made by Ehrlich, also concludes from his researches on sections of the bone marrow of animals in extrauterine life that both kinds of erythrocyte formation occur. Quite recently, Pappenheim, partly in conjunction with O. Israel, has carried out very thorough researches on these particular points. As the subject for observation he chose the blood of embryonic mice. He was able, in the first place, like Rindfleisch, to produce the exit of the nuclei from the cells by the addition of physiological salt solution to fresh blood, and is of the opinion that the exit of the nucleus from the erythroblasts only takes place artificially. In embryonic blood the metamorphosis to erythrocytes occurs exclusively by nuclear destruction and solution within the cell, be it in the case of megalo or gigantoblasts or of cells of the size of the normal red blood corpuscle. The free nuclei that are observed, whose appearance Pappenheim explains by a preceding solution of the protoplasm, plasmolysis, he regards, in opposition to Rindfleisch and Neumann, not as the beginnings of a developmental series, but as the surviving remnants of the degenerated dying blood cells. Clinical observation, certainly, does not support this conception of Pappenheim's, inasmuch as in suitable cases with numerous free nuclei, leukemia, blood crises, transitional forms, which according to Pappenheim must necessarily be present, are not to be found. Moreover, in alluding to a case of leukemia of this kind, this author himself admits that the appearance of free nuclei can be explained in this instance by the exit of the nucleus. Although Pappenheim, as above mentioned, recognizes no difference between megaloblasts and normoblasts in embryonic blood as far as the fate of the nucleus is concerned, he nevertheless decidedly supports Ehrlich's separation of the erythroblasts into these two groups, as two hematogenetically distinct species of cells. He does not regard as distinguishing characteristics the size and hemoglobin content of the cells, although, as we have described above, these are in general different in normo and megaloblasts, for these two properties undergo such great variations as to increase considerably, under certain circumstances, the difficulty of diagnosis of individual cells. The chief characteristic is, as Ehrlich has always particularly insisted, the constitution of the nucleus. The nuclei of cells which are with certainty to be reckoned among the normoblasts are marked by the absence of structure, their sharply defined contour, their intense affinity for nuclear stains. That is by properties which histology sums up under the name pinosis Pfitzner, and recognizes as signs of old age. The nuclei of the megaloblasts are round, shew a good deal of structure, and stain far less deeply. Beta. The clinical differences. Normal blasts are found almost invariably in all severe anemias that are the result of trauma, inanition, or organic disease of some kind. They are, however, mostly rather scanty, so that a preparation must be searched for some time before an example is found. But occasionally, most often in acute but also in chronic anemias, and even in cachectic conditions. Every field shews one or more normoblasts. V. Norden was the first to describe a case in which in the course of a hemorrhagic anemia normoblasts temporarily appeared in such overwhelming numbers in the circulating blood that the microscopic picture, which at the same time comprised a marked hyperleukocytosis, was almost similar to that of myelogenous leukemia. And as in addition to this occurrence the number of blood corpuscles was nearly doubled, V. Norden gave it the distinctive name blood crisis. The following procedure is to be recommended for the investigation of the blood crisis. 1. Estimation of the absolute number of red blood corpuscles. 2. Estimation of the proportion of white to red corpuscles. 3. Estimation of the proportion of nucleated red to white corpuscles by means of the quadratic ocular diaphragm. See page 31, in the dry preparation. For instance, if we find in a case of anemia 3½ millions of red blood corpuscles, the proportion of white to red corpuscles equal 1/100th, and that of the nucleated red to the white equal 1/10th, then in 1 cubic millimeter there are 3,500 nucleated red corpuscles, that is, for 1,000 ordinary there is 1 nucleated corpuscle. Megaloblasts, on the contrary, are never found in traumatic anemias, and in chronic anemias of the severest degree, the result for example of old syphilis, carcinoma of the stomach, and so forth, one looks for them almost always in vain, although they are sometimes to be found in leukemia. On the contrary, the conditions, apparently much milder, in which from the clinical history, etiology, and general objective symptoms pernicious anemia is suggested, are almost without exception characterized by the appearance of megaloblasts in the blood. Nevertheless, in very late stages of the disease they are always scanty, and a very tedious search through one or more specimens is often required to demonstrate their presence. Hence follows the rule, that the investigation of a case of severe anemia should never be considered closed, before 3 or 4 preparations at least have been minutely searched for megaloblasts under an oil immersion objective. This clinical difference between the two kinds of hematoblasts admits of but one natural conclusion, which primarily leaves untouched the question, so much discussed at the present time, whether the megalo or normoblasts can change one to the other. In all cases of anemia in which the fresh formation occurs according to the normal type, only in greater quantity and more energetically, we find normoblasts. Almost all anemias resulting from known causes, acute hemorrhages, chronic hemorrhages, poverty of blood from inanition, cachexias, blood poisons, hemoglobinemia, and so forth, in short all conditions rightly called secondary symptomatic anemias, may shew this increase of normal blood production. In the conditions which Biermer, on the grounds of their clinical peculiarities, has distinguished as "essential pernicious anemia," megaloblasts, on the contrary, occur, and represent an embryonic type of development. The extent to which this type participates in the blood formation in pernicious anemia is most simply demonstrated by the fact that megaloblasts are present in all cases of pernicious anemia, as Locke first shewed, and in some cases form the preponderating portion of the blood discs. Whilst, therefore, in the ordinary kinds of anemia we find that the red corpuscles tend to produce small forms, in pernicious anemia, on the other hand, and exclusively in this form, we find a tendency in the opposite direction. This constant difference cannot be a chance result, but must depend on some constant law. In pernicious anemia excessively large blood corpuscles are produced. Ehrlich's demonstration of megaloblasts has sufficed for this logical advance. All researches which try to obscure or totally deny the distinction between megaloblasts and normoblasts are wrecked by the simple clinical fact that in pernicious anemia the blood is megaloblastic. The appearance of megaloblasts and megalocytes is therefore evidence that the regeneration of the blood in the bone marrow is not proceeding in the normal manner, but in a way which approximates to the embryonic type. The extreme cases are naturally seldom, such as that of Rindfleisch, in which the whole bone marrow was found full of megaloblasts. It is sufficiently conclusive for the pernicious nature of the case. "If only considerable portions, but not the whole marrow, have lapsed into megaloblastic degeneration, we can now say that the megaloblastic metamorphosis is not a purposeful process, and for the following reasons: 1. Since the fresh formation of red blood corpuscles by means of the megaloblastic method is clearly much slower. This is especially borne out by the fact that the megaloblasts are present in the blood always in small numbers only, while the normoblasts, as above mentioned, are often found in much larger quantities. In agreement with this, blood crises are not to be observed in the megaloblastic anemias. 2. Since the megalocytes, which are formed from the megaloblasts, possess in proportion to their volume a relatively smaller respiratory surface, and so constitute a type disadvantageous for anemic conditions. This is still more evident when we remember that the production of poikilocytes is on the contrary a serviceable process. The megaloblastic degeneration of the bone marrow is no doubt due to chemical influences, which alter the type of regeneration in a disadvantageous manner. We do not, for the most part, yet know the exciting causes of the toxic process. Consequently, we are unable to put a stop to it, and its termination is lethal. The Bothriocephalus anemias, which in general, as is well known, offer a good prognosis, by no means contradict this view. They hold their privileged position amongst the anemias of the megaloblastic type only for the reason that their cause is known to us, and can be removed. As in many infectious diseases, individuals react quite differently to the presence of the Bothriocephalus. Some remain well, others show the signs of simple anemia, ultimately with normoblasts, while a third group presents the typical picture of pernicious anemia. For many years, so long as its etiology was unknown, Bothriocephalus anemia was not separated on clinical grounds from pernicious anemia. Severe Bothriocephalus anemia may be described as a pernicious anemia, with a known and removable cause. Good evidence for this point of view is afforded by a case of Ashkenazi, who describes a severe pernicious anemia, with typical megaloblasts, in which after the complete expulsion of the Bothriocephalus, the megaloblastic character of the blood formation quickly vanished, was replaced by the normoblastic, and the patient rapidly recovered. This observation is so unequivocal that it is a matter of surprise that Ashkenazi chooses to deduce from it the ready transition from megaloblasts to normoblasts, whereas it is clear and definite evidence that megaloblasts are only produced under the influence of a specific intoxication, and in this way the presence of megaloblasts in the pernicious anemias is to be explained. The megaloblastic degeneration of the bone marrow depends on the presence of certain injurious influences, of which unfortunately we are as yet ignorant. Were it possible to remove them, it is quite certain a priori that the bone marrow, if the disease were not too advanced, would resume its normal normoblastic type of regeneration. Clinical observation supports this contention in many cases. In megaloblastic anemias, apparent cures are by no means rare, but sooner or later a relapse occurs, and finally leads with certainty to a lethal issue. These cases, familiar to every observer, prove with certainty that the megaloblastic degeneration as such may pass away, and that in isolated cases the conventional treatment by arsenic suffices to bring about this result. A definite cure, however, under these conditions, is not yet attained, since we do not know the etiological agent, still less can we remove it. For this reason the prognosis of megaloblastic anemia, apart from the group of Bothriocephalus anemia, is exceedingly bad. End of Section 3. This section dedicated to Dr. Lewis A. of Tampa, Florida.
Of Histology of the Blood. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Histology of the Blood by Paul Ehrlich and Adolf Lazarus. Translated by M. Myers. Section 5. The white blood corpuscles. The physiological importance of the white blood corpuscles is so many-sided that they form the most interesting chapter of the subject. That the white blood corpuscles play a significant part in the physiology and pathology of man has been recognized but slowly, obviously because there was at first some hesitancy in ascribing important functions to elements that are present in the blood in such relatively small numbers. A place in pathology was first assured to them by Virchow's discovery of leukemia. The interest in the question was increased by Cohnheim's discovery that inflammation and suppuration are due to an emigration of the white blood corpuscles, and these conditions were particularly suitable for throwing light on normal processes. The fact that in diffuse inflammations large quantities of pus are often produced in a short time, without the blood being thereby made poorer in leucocytes, that the opposite indeed occurs, necessitated the supposition that the source of the leucocytes must be extraordinarily productive. Hence, in contradistinction to the red blood corpuscles, their small number is fully compensated by their exceptional power of regeneration. Nevertheless, a considerable time elapsed before the powerful impulse that started from Cohnheim bore fruit for clinical histology. As we have mentioned, this was due to the circumstance that an exact differentiation of the various forms of leucocytes was very difficult with the methods in use up to that time. Although such distinguished observers as Wharton Jones and Max Schultze had been able to distinguish different types of leucocytes, Cohnheim's work remained clinically fruitless, since the criteria they assigned were far too subtle for investigation at the bedside. Virchow, indeed, the discoverer of leukocytosis, interpreted it as an increase of the lymphocytes, whereas it is chiefly produced by the polynuclear cells. Only after the distinction was facilitated by the dry preparation and the use of stains did interest in the white corpuscles increase, and continue progressively to the present day. This is borne out by the exceptionally exhaustive hematological literature, and particularly by that of leukocytosis. In spite of these advances, a retrograde movement in the doctrine of the leukocytes has gained ground surprisingly, especially in the last few years. Ever since Virchow's description of the lymphocytes, observers have tried to separate the various forms of leukocytes one from another, and if possible to assign different places of origin to these different kinds. There now suddenly appears an endeavour to bring all the white blood corpuscles into one class, and to regard the different forms as different stages merely of the same kind of cells. The following sections will show that this tendency is unwarranted and unpractical. 1. Normal and pathological histology of the white blood corpuscles. The classification of the white corpuscles of normal human blood, drawn up by Ehrlich, has been accepted by most authors, and we therefore give a short summary of it, as founded on the dry specimen. 1. The lymphocytes. These are small cells, as a rule approximating in size to the red blood corpuscles. Their body is occupied by a large round homogeneously stained nucleus, centrally situated, whilst the protoplasm surrounds the nucleus as a concentric border. Between nucleus and protoplasm there is often found a narrow areola, which doubtless results from artificial retraction. Nucleus and protoplasm are basophil. Nevertheless, in many methods of staining, the protoplasm possesses a much stronger affinity for the basic stain than does the nucleus. The nucleus in these cases stands out as a bright spot from the deeply stained mass of protoplasm, which is reticulated in a peculiar manner. Within the nucleus are often to be found one or two nucleoli, with a relatively thick and deeply stained membrane. With methylene blue and similar dyes the protoplasm stains unequally, which is not to be considered as the expression of a granulation, as Ehrlich first assumed, but rather of a reticular structure. The contour of the lymphocytes is not quite smooth as a rule, at least in the larger forms, but is somewhat frayed, jagged, and uneven. Small portions of the peripheral substance may repeatedly bud off, especially in the large forms, and circulate in the blood as free elements. In stained specimens, especially from lymphatic leukemia, these forms, which completely resemble the protoplasm of the lymphocytes in their staining, may from their nature and origin be readily recognized. As far as the further metamorphosis of the nucleus is concerned, a sharp notching of the border of the nucleus may occasionally be found, the further fate of which is shown in the accompanying figure. It is evident that in this case the resulting nuclear forms are quite different from those which are characteristic of the polynuclear elements. The protoplasm possesses no special affinity for acid and neutral dyes, and hence in triacid and hematoxylin preparations the small lymphocytes are seen chiefly as lightly stained nuclei, apparently free. In the larger cells the protoplasm can be seen, even in these preparations, to be slightly stained. By the aid of the iodine-eosin method, the reaction of the protoplasm of the lymphocytes is shown to be strongly alkaline. They do not contain glycogen. These properties, taken as a whole, constitute a picture completely characteristic of the lymphocytes, and these elements can thereby be diagnosed and separated from other forms, even when their size varies. Generally speaking, these cells, as above mentioned, are distinguished in the blood of the healthy adult by their small size, approximating to that of the red blood corpuscles. In the blood of children, on the contrary, larger forms are found even in health, and in lymphatic leukemia particularly large forms occur, which are mistaken in various ways by unpractised observers. Thus Trojer's marrow cells still figure in the literature, but have absolutely nothing to do with the marrow. They are large lymphocytes, as was established by A. Freinkel years afterwards. In the normal blood of adults, the number of the lymphocytes amounts to about 22 to 25% of the colourless elements. Increase of the lymphocytes alone occurs, but in comparison with that of the other forms, much more seldom, and will be conveniently called by the special names of lymphocytosis or lymphemia. 2. Sharply to be distinguished from the lymphocytes is the second group, the large mononuclear leukocytes. These are large cells about twice to 3 times the size of the erythrocytes. They possess a large oval nucleus, as a rule eccentrically situated, and staining feebly, and a relatively abundant protoplasm. The latter is free from granulations, feebly basophil, and, in contrast to the protoplasm of the lymphocytes, stains less deeply than the nucleus. This group is present in normal blood in but small numbers, about 1%. They are separated from the lymphocytes because they are totally different in appearance, and because forms transitional between the two are not observed. It cannot yet be decided from which blood-producing organs these forms arise, whether from spleen or bone marrow, although there are many reasons for regarding the latter as their place of origin. These large mononuclear leukocytes change in the blood to the following kind. 3. The transitional forms. These resemble the preceding, but are distinguished therefrom by deep notchings of the nucleus, which often give it an hourglass shape; further, by a somewhat greater affinity of the nucleus for stains, and by the presence of scanty neutrophil granulations in the protoplasm. The groups 2 and 3 comprise together about 2 to 4% of the white blood corpuscles. Footnote: in enumerating the blood corpuscles, 2 and 3 may be counted separately or in one group. End footnote. 4. The so-called polynuclear leukocytes. These arise in small part, as will be described later in detail, from the above-mentioned number 3, within the bloodstream. By far the largest part is produced fully formed in the bone marrow, and emigrate to the blood. These cells are rather smaller than numbers 3 and 2, and are distinguished by the following peculiarities. Firstly, by a peculiar polymorphous form of nucleus, which gives the relatively long, irregularly bulged and indented nuclear rod the appearance of an S, Y, E, or Z. The complete decomposition of this nuclear rod into 3 to 4 small round single nuclei may occur during life, as a natural process. Ehrlich first discovered it in a case of hæmorrhagic smallpox. It is frequently found in fresh exudations. Formerly, when various reagents, for instance acetic acid, were customarily used, the decomposition of the nucleus into several parts was more frequently observed, and Ehrlich for this reason chose the not wholly appropriate name polynuclear for this form of cell. As this name has now been universally adopted, and misunderstandings cannot be expected, it is undoubtedly better to keep to it. The expression cells with polymorphous nuclei would be more accurate. The nucleus stains very deeply with all dyes. The protoplasm possesses a strong attraction for most acid stains, and is unmistakably characterized by the presence of a dense neutrophil granulation. The reaction of the protoplasm is alkaline, to a lesser degree, however, than in the lymphocytes. No free glycogen is contained in the polynuclear cells as a rule. Nevertheless, in certain diseases, cells are always found which give a marked iodine reaction. In this manner, the appearance of cells containing glycogen in diabetes was first proved. Note: Ehrlich, Gabrichewski, Livierato. End note. The iodine reaction in the white blood corpuscles is also seen in severe contusions and fractures, in pneumonias, in rapidly progressing phlegmata from Streptococcus and Staphylococcus, after protracted narcosis. Note: Goldberger and Weiss. End note. Ehrlich explains the appearance of glycogen as follows. The glycogen is not present in the cell as such, but in the form of a compound which does not stain with iodine. This compound readily splits off glycogen, which then gives the iodine reaction. Footnote: The assumption of Czerny that the cells which react to iodine emigrate from suppurating foci is without foundation. A simple investigation of freshly inflamed tissue is sufficient to show that the cells which have wandered from the bloodstream soon contain glycogen. End footnote. We cannot regard the perinuclear green granules described by Nurser in the polynuclear cells as pre-existing. The number of polynuclear leukocytes in the blood of the healthy adult amounts to about 70 to 72% of the total white corpuscles. Note: Einhorn. End note. Footnote: Kanthack described this group as finely granular oxyphil cells. Their granules stain red in eosin and in eosin methylene blue solutions, but the colour is different from that of the true eosinophil cells, and much less intense. In the latter mixture they stain really with the methylene blue salt of eosin. Their true nature is shown by their behaviour with the triacid solution. End footnote. 5. The eosinophil cells. These are characterized by a coarse, round granulation, staining deeply with acid dyes, and similar in other respects to the polynuclear neutrophils. With faint staining, a thin peripheral layer of the eosinophil granule is seen more deeply stained than the interior. The nucleus, as a rule, is not so deeply stained as in the polynuclear neutrophil, but otherwise, in its general shape, is completely similar. Both forms have in common a considerable contractility, which renders possible their emigration from the vessels, and their appearance in exudations and in pus. The size of the eosinophils frequently exceeds that of the neutrophils. Their number is normally about 2 to 4% of the white cells. 6. The mast cells. These are present, though very sparingly, in every normal blood. 0.5% is their maximum number in health. Their intensely basophil granulation of very irregular size and unequal distribution, must specially be mentioned. The granulation possesses the further peculiarity in that, with the majority of basic dyes, it stains not in the pure colour of the dye, but metachromatically, most deeply with thionin. As Dr. Morgenroth found, the deviation from the colour of the dye is still more marked with Cressyl violet R, Mülheim manufactory, when the granules stain almost a pure brown. The staining power of the nuclei is very small, and it is therefore hard to make out the shape of the nucleus without the use of difficult methods. In triacid preparations the granulation is unstained, and the mast cells appear as clear polynuclear cells free from granules. So much for the colourless cells in the blood of the normal adult. In pathological cases, not only do the forms so far mentioned occur in altered numbers, but abnormal cells also make their appearance. To these belong 1. Mononuclear cells with neutrophil granulation. Note: myelocytes, Ehrlich. End note. Generally they are bulky, with a relatively large, faintly staining nucleus, often fairly centrally placed, and equally surrounded by protoplasm on all sides. A fundamental distinction from the large mononuclear cells lies in the fact that the protoplasm exhibits a more or less numerous neutrophil granulation. Besides the larger myelocytes, much smaller forms approximating to the size of the erythrocytes are also found. All transitions between these two stages are likewise met with. In contradistinction to the polynuclear neutrophil elements, these mononuclear forms show no amoeboid movement on the warm stage. They form a constant characteristic of myelogenic leukemia, and in these cases generally occur in large numbers. Reinbach has found them in a case of lymphosarcoma with metastases in the bone marrow. A. Lazarus observed their transitory occurrence in moderate number in a severe post-hæmorrhagic anemia. M. Beck observed them in the blood of a patient with severe mercury poisoning. They are also frequently found in children's diseases, especially in anemia pseudoleukemica infantum. K. Elze established their presence in a boy of 15 months suffering from a slowly progressing tuberculosis of the lymphatic glands. The appearance of myelocytes in infectious diseases is particularly interesting. Ryder had previously demonstrated that myelocytes may be present in acute inflammatory leukocytoses, and recently a thorough work by C.S. Engel has appeared upon the occurrence of myelocytes in diphtheria. Engel discovered the interesting fact that myelocytes are often to be found in children suffering from diphtheria, and further made the important observation that a high percentage of myelocytes, note 3.6 to 16.4% of the white elements, end note, only occurs in severe cases, and points to an unfavourable prognosis. Myelocytes are also present in mild cases, though not constantly, and in much smaller number. Türk has recently undertaken a very exact and thorough analysis of their occurrence in infectious diseases, in the course of which he accurately tabulated the white corpuscles in a large number of cases. The results he obtained in pneumonia are especially characteristic, for he found at the commencement of the disease that myelocytes are not seen at all, or only very scantily, and it is only at the time of the crisis, or directly afterwards, that they become specially numerous. In isolated cases the increase at this time was very considerable, and in one case amounted almost to 12% of all neutrophil cells. 2. Mononuclear eosinophil cells. Note: eosinophil myelocytes. End note. H. F. Müller was the first to point out their importance. They constitute the eosinophil analogue of the previous group, and are much larger than the polynuclear eosinophils. Medium and small-sized examples are often found in leukemia. Eosinophil myelocytes are almost constantly present in myelogenous leukemia and in anemia pseudolymphatica infantum. Apart from these two diseases they are very rarely found. Mendel saw them, for example, in a case of myxedema, Türk quite exceptionally in some infectious diseases. 3. Small neutrophil pseudolymphocytes. They are about as large as the small lymphocytes. possess a rounded, deeply stained nucleus and a small shell of protoplasm studded with a neutrophil granulation. The relatively deep stain of the nucleus and the small share of the protoplasm in the total cell body prevent confusion with the small forms of myelocytes, which never reach such small dimensions. The neutrophil pseudolymphocytes are exceedingly infrequent and represent products of division of the polynuclear cells. They were first described by Ehrlich in a case of hæmorrhagic smallpox. The process of division goes on in the blood in such a manner that the nuclear rod first divides up into 2 to 4 single nuclei, and then the whole cell splits up into as many fragments. These cells occur also in fresh pleuritic exudations. After a time the nucleus of these cells becomes free, and the little masses of protoplasm thus cut off are taken up mostly by the spleen substance. The free nucleus likewise shares in the destruction. It is of the greatest importance that these cells, which up to the present have not elsewhere been described, should receive more attention. They must be of significance, in particular for the question of transitory hyperleukocytosis, which is by some referred to as a destruction, by others to an altered localization of the white blood corpuscles. 4. Stimulation forms were first described by Türk, and are mononuclear non-granulated cells. They possess a protoplasm staining with various degrees of intensity, but in any case giving with triacid solution an extraordinarily deep dark brown, and further a round simple nucleus, often eccentrically situated, stained a moderately deep bluish green, with, however, a distinct chromatin network. The smallest forms stand between the lymphocytes and the large mononuclear leukocytes, but approach the first named, as a whole, in their size and general appearance. According to Türk's investigations, these cells often appear simultaneously with, and under the same conditions, as the myelocytes. Their importance cannot at present be accurately gauged. Possibly they form an early stage of development of the nucleated red blood corpuscles, as the deeply staining and homogeneous protoplasm seems to indicate. With the description of these abnormal forms of white corpuscles, all occurring forms are by no means exhausted. We are here excepting completely the variations in size which particularly affect the polynuclear and eosinophil cells, and which lead to dwarf and giant forms of them. For, however considerable the difference in size, these cells always possess characteristics sufficient for an exact diagnosis. But besides these, isolated cells of an especially large kind are found, particularly in leukemic blood, and concerning their importance and relationship we are, up to the present, in the dark. End of section 5. Of Histology of the Blood. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Histology of the Blood by Paul Ehrlich and Adolf Lazarus. Translated by M. Myers. Section 6. On the places of origin of the white blood corpuscles. For the comprehension of the histology of the blood as a whole, it is of great importance to obtain an exact knowledge how and to what extent the three organs which are undoubtedly very closely connected with the blood, lymphatic glands, bone marrow, and spleen, contribute to its formation. The most direct way of deciding the question experimentally, by excision of the organs in question, is unfortunately only available for the spleen. The part played by the lymphatic glands and bone marrow, whose exclusion in toto is not possible, must mainly be determined by anatomical and clinical considerations, but only by a careful combination of experiments on animals, of anatomical investigations, and especially of clinical observations on a large scale, can light be thrown on these very difficult questions. It cannot be emphasized sufficiently how important it is that everyone engaging in haematological work should first of all collect a large series of general observations, otherwise errors are bound to occur. For instance, the endeavour is often made to compensate the lack of personal experience by careful literary studies, but in this way the histology of the blood falls into a vicious circle, of which the new phase of blood histology affords many examples, and it is characteristic of this kind of work that from the investigation of a single rare case, most far-reaching conclusions on the general pathology of the blood are at once drawn, e.g. Troja's paper, in which, having failed to recognise the lymphocytic character of a case of leukemia, and believing therefore that he had to do with a myelogenous leukemia, the author denied and completely reversed all that had been previously established about this disease. It is equally hard to avoid errors if one confines oneself exclusively to animal experiments without supplementing these by clinical experience, as is shown by the numerous papers of Uskoff. Not the anatomist, not the physiologist, but only the clinician is in the position to discuss these problems. In the introduction to this chapter we have already alluded to the striking retrograde movement in haematology at the present time, brought about by the view that the white corpuscles as a whole are derived from the lymphocytes. If we disregard the embryological investigations on this point, note Saxa, end note, anatomists, physiologists, and clinicians alike have taken up a similar point of view. Among anatomical papers we may refer to those of Gulland, according to whom all varieties of leukocytes are but different stages of development of one and the same element. He distinguishes hyaline, acidophil, and basophil cells, and derives all from the lymphocytes. Arnold advocates similar views, though in a negative form. He says that a distinction between so-called lymphocytes and the leukocytes with polymorphous nuclei, on the grounds of the form of the cell and nature of the nucleus, is not possible at the present time. Neither is a classification based on the granules admissible, since the same granules occur in different cells, and different granules in the same cell. The work of Gulland and Arnold takes into consideration the differential staining of the granules in various ways. In spite of their facts, we disagree with their conclusions, and we shall therefore have to analyse them in the special description of the granulated cells and granules. Recently, since 1889, Uskoff has in particular published experimental work in this province of haematology. This has led him to see in the white blood corpuscles the developmental series of one kind of cell, and to distinguish in it three stages: 1. Young cells, which correspond to our lymphocytes; 2. Ripe cells, note globule Moore, end note, large cells with fairly large and irregularly shaped nucleus, which are therefore our large mononuclear and transitional forms; 3. Old cells, note globule Vieux, end note, which represent our polynuclear cells. The eosinophil cells are completely excluded from this classification. Amongst clinicians, A. Frankel has recently gone in the same direction, and, on the grounds of his experience in acute leukemias, has supported the view of Uskoff that the lymphocytes are to be regarded as young cells and early stages of the other leukocytes. But few authors, note for instance C.S. Engel, Ribbert, end note, have raised a protest to this mixing of all cell forms of the blood, and have held to the old classification of Ehrlich. But as it is emphatically taught in numerous medical works that all these cells are closely related, the grounds for sharply separating the lymphocytes from the bone marrow group may here be shortly summarized, and stress laid on the great importance which this apparently purely theoretical question has for clinical observation. We shall come to most important conclusions about this point when we consider more closely the share which the various regions of the haematopoietic system take in the formation of the blood, and especially of the colourless elements. Alpha. The spleen. The question whether the spleen produces white blood corpuscles has played a large part from the earliest times of haematology. Endeavours were first made to investigate the participation of the spleen in the formation of the white blood corpuscles by counting the white blood corpuscles in the afferent and efferent vessels of the spleen. It was thought that the blood-forming power of the spleen was proved by the larger number of corpuscles in the vein as compared with the artery. The results of these enumerations, however, are very varying. The investigators who found a relative increase in the vein are opposed by other investigators equally reliable, and, with the experience of the present day, one would not lay any value on these experiments. We must emphasize the fact, established by later researches, that after extirpation of the spleen, an enlargement of various lymphatic glands occurs. The alterations of the thyroid, which have been observed by many authors, cannot be described as constant. Further, the blood investigations which Mosler, Robin, Winogradau, Zersas, and others have carried on in animals and man after removal of the spleen must here be mentioned. These have already proved that a leukocytosis occurs after some considerable time. Professor Kurloff carried out detailed investigations in 1888 in Ehrlich's laboratory, and carefully studied the condition of the blood after extirpation of the spleen. As the work of Professor Kurloff has so far only appeared in Russian, his important results may be here recorded more fully. For his researches, Kurloff employed the guinea pig, as this animal by its peculiar blood is specially suited for this purpose. In order to give a systematic account of the results of these important investigations, we must first shortly sketch the normal histology of the blood of the guinea pig, according to Kurloff. In the blood of the healthy guinea pig the following elements are found. 1. Cells bearing granules. 1. Polynuclear with pseudoeosinophil granulation. This granulation, which Ehrlich had previously found in the rabbit, is easily distinguishable from the true eosinophil, since it is much finer and stains quite differently in eosin-aurantia-nigrosin mixtures. One principal distinction between these two forms of cells lies in the fact that, according to Kurloff, this granulation is very easily dissolved by acid, but remains unchanged in alkaline solutions. Doubtless an indication that the granulation consists of a basic body, soluble with difficulty, which with acids forms soluble salts. The true eosinophil granulation remains, on the other hand, quite unchanged under these conditions. These pseudo-eosinophil polynuclear cells correspond functionally to the neutrophil polynuclear of man. Their number amounts to 40 to 50% of the total white cells. The red bone marrow is to be regarded as the place of origin of this kind of cell. It contains very many pseudo-eosinophil cells, and indeed all stages are to be found in it, from the mononuclear cells bearing granules to the fully formed polynuclear. 2. The typical eosinophil leukocytes, which fully correspond to those found in man, and amount to about 10% of the number of the white. 3. The nigrosinophil cells, as they are called by Kurloff. In their general appearance, in the size of the cell and the granulation, they completely correspond to the eosinophil cell. The only distinction between them consists in a chemical difference in the granulation. These cells stain in the colour of nigrosin in the aurantia-eosin-nigrosin mixture, whilst the eosinophil cells become red. The two granulations always show different shades in the triacid preparation as well, for the nigrosinophil cells stain a blacker hue. 2. Cells free from granules. Alpha. Cells with vacuoles. This is a quite peculiar group, characteristic for the blood of the guinea pig. It shows transitions in the blood from large mononuclear to transitional and polynuclear forms, but is marked by the lack of any kind of granulation. Instead of the latter, we find in these cells a roundish, nucleus-like form in the protoplasm, which also takes on the nuclear stains, and possibly is to be considered an accessory nucleus. We have received the impression that we have here to deal with a vacuole filled with substance secreted by the cells. In a large series of preparations it is possible to obtain some elucidation of the development and fate of these appearances. They first appear as point-like granules in the protoplasm, bearing no relation to the cell nucleus. They gradually increase, and acquire a considerable circumference. When they have attained about the size of the cell nucleus, they, or rather their contents, appear to break through the protoplasmic membrane and to leave the cell. The number of the vacuole-containing cells is 15 to 20% of the colourless blood corpuscles. Beta. Typical lymphocytes. Their appearance completely corresponds with that of human lymphocytes as described above. They make up 30 to 35% of the total number of leukocytes. Now Kurloff, in the course of extremely careful and laborious researches, estimated the total number of leukocytes, and then from the percentage numbers the total quantity of pseudo-eosinophil, neutrophil, eosinophil, vacuole-containing cells, and lymphocytes, and could thus demonstrate that in uncomplicated cases of removal of the spleen, where inflammatory processes, accompanied by an increase of the polynuclear neutrophil corpuscles, were avoided, a gradual increase of the lymphocytes alone in course of time results. This may be a 2- or 3-fold increase, whereas the numbers of all other elements remain unchanged. Kurloff obtained his figures as follows. First he estimated the relative proportions of the different kinds of white blood corpuscles, one to another, in a large number of cells, 500 to 1,000. Account of this kind, however, gives no evidence as to whether one or other kind of cell is absolutely increased or diminished. A fall in the percentage of the lymph cells may be brought about by 2 quite different factors. 1. By a diminished production of lymphocytes. 2. By an increased influx of polynuclear forms, which naturally lowers the relative count of the lymphocytes. It was therefore necessary to obtain a method which would show alterations in the absolute number of the individual forms of leukocytes. Kurloff used for this purpose the comparative field. That is, he counted by the aid of a movable stage the different forms which lay on a definite area, 22 square millimeters, of the dried blood preparation. This procedure gave very exact results, as only faultlessly prepared and regularly spread preparations were used. The following figures, from experiment 2, illustrate the method and its results. April the 12th, 52% pseudo-eosinophils. September the 2nd, 1 month after the operation, 22% pseudo-eosinophils. April the 12th, 10% lymphocytes counted. September the 2nd, 53% lymphocytes counted. By the end of the comparative surface, these figures were supplemented by the following averages. On each surface used for comparison were found April the 12th, 38 white, consisting of 19.8 pseudo-eosinophils, 10.6 lymphocytes. September the 2nd, 81 white, consisting of 18.0 pseudo-eosinophils, 46.9 lymphocytes. From this example it follows without doubt that the total number of the white blood corpuscles had about doubled itself, but that in this increase the lymphocytes exclusively were concerned, and the pseudo-eosinophil cells had not undergone the smallest increase. The results which Kurloff obtained by means of this method in animals whose spleens had been removed may be illustrated by one of his original researches and its accompanying chart and table. Experiment 1. Young female. Weight 234 grams. Number of red corpuscles in a cubic millimetre of blood 5,780,000. Number of white 10,700. On April the 19th, 1888, the spleen was removed, the wound healed by first intention. The results of the further investigation of the blood are found in the following table. From the chart and table, the number, on the surface of comparison, of the white blood corpuscles is seen to have more than doubled itself in the first 7 months, and that this increase was solely dependent on the flooding of the blood by lymphocytes. The nucleated or bone marrow elements and the large mononuclear cells remained continuously at the same level during the whole period. The changes in the percentage proportions ran somewhat differently. The percentages rose from 35 to 66% for the lymphocytes only, whilst for the other forms they distinctly fell, for the nucleated from 44% to 22%, and for the large mononuclear from 18% to 9%. It was only in the course of the second year that a very considerable relative and absolute increase of the eosinophil cells appeared. The values rose gradually from about 1% to 28.9%, or from 0.5 to 13.9 on each comparison area. The last examination of the blood in this animal was made on April 30th, 1890, that is, 2 years after the removal of the spleen. The animal was quite healthy, bore 4 healthy young guinea pigs by a father whose spleen had been removed. The young have a completely normal spleen, and their blood likewise shows no abnormalities. Reader's note: Table 1, showing cell numbers and proportions on 26 dates from April the 19th, 1888 to April the 30th, 1890, is omitted. End reader's note. The results of further investigations, which we here shortly repeat in tabular form, show that in this experiment No. 1 we are not dealing with an abnormal phenomenon of an exceptional animal. Experiment 1. Before splenectomy, 10,700 white blood corpuscles. At the end of the first year, 14,200. At the end of the second year, 18,000. Experiment 2. Before splenectomy, 12,000 white blood corpuscles. At the end of the first year, 27,600. At the end of the second year, 32,000. Experiment 4. Before splenectomy, 15,000. At the end of the first year, 19,200. At the end of the second year, 19,000. Average: before the splenectomy, 12,600. At the end of the first year, 20,333. At the end of the second year, 23,300. By estimating the percentage proportion of the single kinds of white blood corpuscles, Kurloff obtained the following result. Reader's note: table omitted, showing cell counts for 5 different cell types before operation, at the end of the first year, and at the end of the second year for 3 experiments. End reader's note. From these researches we draw the following conclusions. 1. The spleen is not an indispensable, vitally important organ for the guinea pig, since that animal bears splenectomy without loss of health, develops normally, and gains well in weight. 2. The hypertrophy and hyperplasia of the lymph glands, particularly of the mesenteric glands, which develop after the operation, correspond to a lymphocytosis, which makes its appearance in the course of the first year after the operation so constantly that it may be looked upon as a characteristic sign of the absence of the spleen. This increase may amount to double and more. We must therefore assume that the deficiency of splenic function may be met by the lymphatic glandular system. This period of lymphemia may doubtless in some animals persist for years in exceptional cases. In the majority, however, the lymphemia diminishes in the course of the first year, and indeed subnormal quantities of lymphocytes may then be produced. 3. The cells of the bone marrow, on the contrary, and the polynuclear pseudoeosinophil cells do not show the least variation in the course of the first year. Bearing in mind that under normal conditions these cells are met with exclusively in the bone marrow, and that inflammation in animals after removal of the spleen is accompanied by an acute pseudoeosinophil leukocytosis, exactly as in normal animals, one must admit that the production and function of this kind of cell are quite independent of the spleen. Hence there can be no doubt about their myelogenic nature. 4. It is especially important that the mononuclear, and the leukocytes associated with them, undergo no increase. As these cells under normal circumstances occur both in the spleen and in the bone marrow, we must assume that normally also the bone marrow is responsible for the majority of this kind in the blood, and that the deficiency in the splenic contribution can be easily covered by a slightly raised activity of the bone marrow. Were the share of the spleen important, from general biological considerations an overproduction of the kind of cell in question must occur in the vicarious organs. 5. The increase of the eosinophil cells, which constantly makes its appearance in the second year after the operation, is highly interesting, and leads to a really enormous rise in their absolute and relative numbers. Their percentage number once rose to 34.6%, and their absolute quantity amounted at the end of the second year, on the average, to 30 to 50-fold their original number. Hence it follows from Kurloff's researches that the spleen of the guinea pig plays quite an unimportant part in the formation of the white blood corpuscles, and that after splenectomy in the first year, compensation occurs only in the lymph glands, followed in the second year by a great increase of the eosinophil cells. It is to be particularly insisted, once again, that the spleen has nothing at all to do with the formation of the pseudo-eosinophil polynuclear cells, which are the analogues of the polynuclear neutrophils of man. How do observations on man stand in the light of Kurloff's observations? which might be regarded as depending on peculiarities of the particular kind of animal. Completely analogous material is afforded by cases in which in healthy people a splenectomy has been necessary in consequence of trauma. Unfortunately, the material available for this purpose is extremely rare, and it would be of the utmost value if the alterations of the blood in such a case were systematically studied for a period of years. We have ourselves begun our observations in 2 patients directly after the operation, but were unable to continue them, as death occurred within the first week after the extirpation. Up to the present, only 7 cases of rupture of the spleen with subsequent splenectomy have been published, as is stated in the collection of cases of V. Beck. In 2 only of these 7 cases, one of Reicher's, Breslau, the other of V. Beck's, Karlsruhe, was a cure effected. Through the courtesy of the above-mentioned gentleman, we were able to investigate specimens from these 2 patients. In the case of V. Beck, the operation was performed on June 15th, 1897. We received a dry blood preparation about 6 months after operation. Investigation showed a considerable lymphemia. The bulk of the lymphocytes belonged to the larger kinds. The eosinophil cells were certainly not increased. For other reasons, an exact numerical analysis could not be undertaken. We hope to be able to follow the further course of this case. In the second case, the operation was performed on May 17th, 1892, by Dr. Reicher of Breslau, for trauma, and later described. We made counts in oldish and fresh preparations. It is worthy of notice that this case is not uncomplicated, as an amputation of the thigh was performed shortly after the splenectomy on account of gangrene. We found the following figures. Preparations from June 12th, 1892, polynuclear 81.9%, October 11th, 1892, 80.0%, September 1897, 56.8%. Lymphocytes from June 12th, 1892, 15.9%, October 11th, 1892, 13.7%, September 1897, 33.1%. Eosinophil from June 12th, 1892, 1.3%, October 11th, 1892, 4.0%, September 1897, 3.5%. Large mononuclear, June 12th, 1892, no data. October 11th, 1892, 1.7%, September 1897, 1.5%. It is much to be regretted that dry preparations only, at the beginning and at the end of the 5-year period of observation, were at our disposal. It appears from the paper of Reicher as if, in this case, the lymphocytosis had established itself 1 month after the operation, and had lasted for a very long time, just as Kurloff has found in some animal experiments. Just as little as a polynuclear increase is abnormal, is an increase of the lymphocytes remarkable, and in this case the lymphocytic increase was recognizable after the end of the 5th year. The eosinophil cells oscillate at this period about the upper normal limit. From all that we know, it is probable that their number in the meantime had undergone an intercurrent increase. The cases are more frequent in which a splenectomy has been undertaken on account of disease of the spleen. Amongst these, the clearest results are a priori to be expected from splenic cysts, since the part of the spleen not affected by the cyst formation often shows quite a normal structure, and therefore is physiologically active. On the other hand, the excision of chronic splenic tumours may be, for the blood condition, of no importance, inasmuch as the function of the spleen may have previously long been eliminated by pathological changes. Among these cases we must in the first place mention the well-known and carefully investigated case of B. Creder. In a man 44 years of age, the spleen was extirpated on account of a large splenic cyst. Within 2 months of the operation there developed a thoroughly leukemic condition of the blood, exclusively brought about by the increase of the lymphocytes, as is seen from the results of Creder and the table contained in his paper. It is further remarkable that 4 weeks after the operation a painful, doughy swelling of the whole thyroid appeared, which remained with variations for nearly 4 months. With the general recovery of the patient, this shrank to a small remnant. We notice further that this very interesting swelling of the thyroid which doubtless stands in the closest connection with the splenectomy, is nevertheless no constant accompaniment of this operation, as for instance in the case of V. Beck, where it was not present. The most recent work on extirpation of the spleen for tumours is from Hartmann and Vasquez. As the result of their researches, the authors arrive at the following conclusions. 1. A slight post-operative increase of the red blood corpuscles, and a true acute hyperleukocytosis occur, and pass rapidly away. 2. The hæmoglobin equivalent of the corpuscles sinks at first, but recovers its original value by degrees. 3. 4 to 8 weeks afterwards, a lymphocytosis of varying duration is established. 4. Later, after many months, a moderate eosinophilia occurs. We have ourselves been able to investigate 3 conclusive cases. The first was a patient which we were ourselves enabled to investigate by the courtesy of Dr. A. Newman. The patient's spleen was removed by E. Hahn on account of an echinococcus on February the 5th, 1895. One may well assume that before the operation the spleen no longer discharged its normal function. On September the 2nd, 1897, we found the following numerical proportions: polynuclear neutrophil 76.5%, lymphocytes 18.4%, eosinophil 3.4%, large mononuclear 1.1%, mast cells 0.4%. A condition, therefore, which was quite normal. In this connection it must be mentioned that an incipient phthisis pulmonum existed at the time, to which we must attribute an increase of the polynuclear elements, and without which the percentage figures of the lymphocytes and eosinophils would perhaps have been greater. For the knowledge of the 2 other cases we are indebted to the kindness of Professor Giunescu of Bucharest. The one case was of a man of about 40 years of age, in whom splenectomy was undertaken on September the 27th, 1897, for an enlarged spleen, healing by first intention. The white blood corpuscles were permanently increased. The proportion of white to red was 1 to 120 to 1 to 130. The average number of red was 3 million. Our own examination of preparations obtained some 2 months after the operation showed a distinct lymphemia, and also a preponderance of the larger lymph cells. The eosinophil and mast cells were plainly increased. We are unable to give more exact numerical data, as the preparations sent to us were not spread with sufficient regularity. From the second case, which was also operated upon for enlargement of the spleen, we unfortunately only obtained much damaged preparations. Nevertheless, so much could with certainty be established that there was no considerable increase of the lymphocytes. The eosinophils, on the contrary, were increased distinctly, the mast cells to a lesser extent. It is probable that the increase of both of the latter kinds of cell was not a consequence of the extirpation of the spleen alone, but rather the expression of the reactive changes which had already begun before the operation, from the exclusion of the splenic function. Cases of splenectomy of this kind are transitional to the chronic diseases of the spleen. The latter present great difficulties, for one never knows how far, in the most chronic diseases, the other organs are damaged or influenced by the general illness. An increase of the lymphocytes, so long as an affection of the lymphatic glands may be excluded, should be referred to functional exclusion of the spleen. On the other hand, an increase of eosinophil cells associated with a chronic tumour of the spleen is analogous to Kurloff's secondary reaction of the bone marrow. Such cases are frequently found in the literature. For instance, Mueller and Ryder bring forth 3 cases of splenic tumour caused by congenital syphilis, cirrhosis of the liver, neoplasm in the cranial cavity, and in which the numbers of the eosinophils amounted to 12.3%, 7.0%, 6.5% respectively. In 3 cases of acute splenic tumour in typhoid fever, the figure 0.31%, with a maximum of 0.82%, was found. These authors have already raised the question whether the increase of the eosinophil cells is connected with the splenic tumour or the bone marrow. Perhaps the functional activity of the latter is vicariously raised to meet the more or less complete exclusion of the spleen from the formation of the blood, since Ehrlich has distinctly asserted that the probable place of formation of the eosinophil cells is the bone marrow. From what has been brought forward, no doubt can now remain that the question has been decided quite in Ehrlich's favour. But what then are the physiological functions of the spleen, since that organ is unnecessary for the persistence of life? Doubtless its chief duty is the taking up of the greater part of the decaying fragments of red and white blood corpuscles in the blood stream, so that this valuable material is not quite lost for the organism. Thus Ponfick has found that after destruction of the red corpuscles the spleen takes up a portion of their shadows, and for this reason calls the splenic tumour a spodogenous splenic tumour. Note, Greek spodos, ruins. End note. Ehrlich has made a corresponding observation for the products of dissolution of the white blood corpuscles, and has proved that the splenic tumour which occurs in many infectious diseases, and in phosphorus poisoning, is to a large extent caused by the parenchyma of the spleen taking up the remains of the neutrophil protoplasm. The question of the relation of the spleen to the fresh formation of red blood corpuscles is a problem of comparative anatomy. Observations on this point made on one kind of animal can certainly not claim validity for other kinds. In lower vertebrates, as in fishes, frogs, tortoises, and also in birds, the blood-forming activity of the spleen is pronounced and of great importance. In mammalia, on the other hand, in some cases this function cannot be demonstrated, and in others only to a very small degree. In the spleen of normal mice, nucleated red blood corpuscles are seen in relatively large numbers. In the rabbit they are less numerous, and often only to be found with difficulty. In the dog they only make their appearance after anemia from loss of blood. Normally they are absent. In the human spleen, nucleated red blood corpuscles are not to be found normally, or in cases of severe anemia, but exclusively in leukemic diseases. U. Gaby, in his recently published work on the hemolytic function of the spleen, also emphasizes the difference between the various animal species. In guinea pigs he found that the spleen acts largely as a scavenger of the red blood corpuscles, in rabbits very slightly. Consequently, after removal of the spleen in guinea pigs, the number of red blood corpuscles rose 377,000 in the cubic millimetre, and the amount of haemoglobin 8.2%. After splenectomy in rabbits, the increase in these values is absent. Shortly summarizing our analysis of the facts before us, we must say that the importance of the spleen for the production of the white blood corpuscles can in no respect be considerable, and that if these cells really are produced by it, they must be free from granulations. The spleen, therefore, stands functionally in closer connection with the lymphatic gland system than with the bone marrow. The spleen has not the least connection with ordinary leukocytosis. Footnote: C.S. Engel has recently proposed to call acute leukocytosis lienal leukocytosis, in analogy with the clinical idea of a lienal leukemia. This terminology should only be used if the polynuclear cells did in fact arise from the spleen, an assumption which Engel himself does not once appear to make, since he expressly warns against drawing any conclusion from this name as to their origin. Since, however, the acute leukocytoses, as we shall show in the next section, are exclusively to be referred to the bone marrow, the term lienal leukocytosis seems to us quite mistaken, for it must logically lead to a conception of the origin of the leukocytes exactly opposed to their actual relationships. End of section 6.